Hello, today I'm presenting you the results of the work conducted with Professor Vasile titled Discovering Unmodeled Components in Astrodynamics with Symbolic Regression. The reasons for such a work are multiple, the main one being the increasing availability of tracking data of both artificial and natural objects. With artificial we mean both operating satellites and space debris, and with natural you can think of asteroids and near-Earth objects in general. Because of this, we're interested in developing a data-driven approach to astrodynamics. Also building on work such as the ones by Koopman and von Neumann, which, while they were first developed in the context of ergodic theory in dynamical systems, are now gaining a lot of traction because of their natural compatibility with the powerful techniques of artificial intelligence, as opposed to the more traditional geometric point of view initiated by Poincaré. So with this in mind, we're interested in autonomously identifying governing equations in astrodynamics. This data-driven approach is actually not new. In fact, the most important book by Kepler, it's called A New Astronomy from Observations of Mars. So the new part, let's say, is the automation part. To do this, we're proposing a genetic programming-based symbolic regression algorithm. The reason for this is that we want to get a symbol as a solution out of the routine, as opposed to, for example, the introduction of empirical acceleration in orbit determination. Moreover, we want to be able to interpret the results, so we're not making use of black box representations such as feed-forward neural networks. And finally, as opposed to popular sparse regression techniques in dynamical systems, we don't need to make that many assumptions on the structure of the solution. So, briefly, symbolic regression aims at building a tree-like structure as the one given here, in which the terminal nodes are symbols that can be associated to some variables, and the other nodes have some operations applied to these symbols that lead to a symbolic expression. Our problem can be stated as an initial value problem in which f is known and we want to determine the perturbing force acting on the system. And in general, this perturbing term can be a function of the state, of a set of parameters, and of time itself. But here we're focusing on time-independent perturbations, so we can get rid of the explicit time dependence. Moreover, it's worth mentioning that we're making use of single-gene genetic programming because of the additive nature of the perturbing term, even though the use of multi-gene in this context has a lot of advantages, let's say. So the implementation has been performed using the distributed evolutionary algorithms in Python library, and the code of this work is publicly available on the GitHub linked here. And the reason for this choice is that the deep library allows for strongly typed genetic programming, meaning that the terminal nodes, the symbols used introduced as inputs for the algorithm, can be associated to a certain type. In this way, it's possible to work with vector-like objects and with scalars, and at the same time introduce type-specific operations. For example, we want to constrain the algorithm to apply the norm operator to vectors, and while still being able to deal with scalars. Getting into the details of the implementation, each simulation presented in this work makes use of a population of 20 individuals randomly initiated. We use the gen half and a half function given in DEEP to do this. The evolution process, combining crossover and mutation operations only, has been performed for 10 generations, leading to a computational time of approximately 1 hour on a single core 2.4 GHz processor. The deep library nevertheless easily enables parallelization, which has been now implemented in the toolbox, leading to a substantial reduction of computational times. The building blocks of the individuals are, as said, a number of symbols representing the system state, position and velocity separately, and constant parameters used as terminal nodes. The operations considered are the sum between scalars, the multiplication constraint to take a scalar and a vector as inputs, the Euclidean norm operator returning a scalar from a vector, the exponential operator working on scalars only, and then a user-defined function called CM that's returning the mth component of an input vector. Since in our case study we are dealing with two-dimensional vectors, just two different user-defined functions have been introduced. The mating operation used is a user-defined combination of the cx1 point and cx1 point lift biased function given in deep. Every time a mating operation is performed, there is a 50% chance of performing one of the two built-in schemes. As far as the mutation scheme is concerned, only one function has been considered. That is the mut insert function, given in deep again. This function inserts a new branch at a random position in a chosen individual. During the evolution, the probability of performing mutation and crossover are user-defined and have been set to 0.2 for each of the two operations. So a challenge of this algorithm is dealing with the fact that we are optimizing both a combinatorial problem, in the sense that we are optimizing the structure of the equation of the tree of the individual, but also we want to find the real value of the parameter that's optimizing our problem. So we have these two different aspects of the problem, and to deal with this we are simply performing a nested optimization in which every time we evaluate an individual, we perform a sensitivity analysis on the set of parameters characterizing the individual to find the optimal value of the real parameters. So the fitness function is defined as the average root sum square of the observation prediction mismatch. And now that we have all the ingredients, we can introduce the case study, which is a perturbed two-body problem. As said, that we're dealing with autonomous perturbations, so we're simplifying the perturbing term in the sense that both the density and the ballistic coefficients are considered to be constant in time. And associated to this case study, here are the solutions. We gave sparse measurements of all the state components, in particular 2 observations per revolution of the spacecraft. And the algorithm was able to correctly identify the structure of the missing term. In fact, reading the drag component in a vector form, you can see it's just a constant times the norm of the velocity vector times the velocity vector itself, which is exactly the structure of the tree that we get out of the algorithm. After this, we introduced noise on top of observations. This has been modeled with Gaussian distributions centered at the nominal value of the observation and using different ranges for the value of the standard deviation. Synthetic measurements have been therefore obtained sampling a given distribution, and the procedure has been repeated for each noise level 35 times, leading to a different optimal solution for each set of noisy observation. Repeatability is maintained by the explicit definition of a random seed at the beginning of the script, even though the process is inherently random. So with a low noise level, the two different families of solutions have been identified. The first one is the correct one, obtained from less than half of the simulations. The other one is a simplified version of the correct one. Indeed, substituting the norm of the velocity vector with a constant, this structure arises. This approximation is understandable by the fact that the drag perturbation leads to a small variation of the norm of the velocity vector, leading to low values of the fitness and a high correlation between the fitness and the extrapolation performance index given in the figure. With even higher noise levels, the results are comparable in the sense that we have increasing values of the fitness and a lowering correlation between it and the extrapolation performance index, but the same families of solution arise. This is true with the exception of a couple of results in which the algorithm was not able to converge. Another important thing to highlight before concluding is that here we're not requiring any estimation of the state derivative of the system. We're just taking into account the observations themselves, and we are able from there to estimate the missing term of the dynamics. And that's all. Let me please acknowledge briefly the Stardust Reloaded network I'm part of that supported this work. We are working on putting together aerospace engineering and dynamical systems theory with artificial intelligence, and if you're interested, please take a look at the website. And that's all for me. Thank you for your time.